Okay, so maybe I'll send an email and I send a message to WhatsApp and then we book things tonight. There's a possibility that I will pay for it, but it's not 100% guaranteed. Okay, anyways.
I'm ready. Okay, so thank you everybody. Today we have Yannik Schüler from Sheffield and we speak about the logical. Yeah, before I start, I want to thank all the organizers for giving me the opportunity to talk here. Yeah, last week was already awesome. And yeah, I'm very much looking forward to this week. Yes, as my title already says, I'm going to talk about the open correspondence and to give some context. Okay, this didn't work this time. Okay, so that's the context. Right. Maybe you remember from last Friday, there is the famous, okay, maybe it becomes famous. Honestly, I think maybe the name will die after this week. The LQ correspondence, where the log, and the open are, I guess, the three letters, and I think we had all before function and river invariants. So, I mean, all these invariants enjoy some qualities, and today we will talk about that. Yeah, I should probably mention that this is yeah, these are results based on work I did together with Andrea and me, but most of the results I will actually show here are results by Sheffield, which is today audience and and Andrea. Okay, so the rough outline of my talk. So what I want to talk about today is correspondence between these invariants. Log, and open invariants are associated with three different geometries, and we don't just take any arbitrary geometries. We will I will explain how these are constructed in a very particular way from a set dimensional geometry. And if all these definitions are done in the correct way, what happens is that all these invariants, which are rational numbers, and curve counts of Gromov Witten type happen to be equal up to some small factors, which I think we can all disregard. I think they didn't spoil this beautiful picture too much. Okay, and yeah, this is also roughly the structure of my talk. So first I will introduce geometry, and then the invariants, and then get our hands dirty and look at how equal they actually are. Okay, so the initial geometry for all our construction is the so-called Yannik pair. It consists of a smooth rational projective complex set Y and the divisor B, whose irreducible components we always write out label as 1 up to PL. And we assume that this divisor is an anti-canonical singular logarithmic. And I have to introduce the more notation, maybe the notion of net Yannik pairs. There we just add the extra condition that all these irreducible components are net divisors. Okay, I already threw a lot of adjectives at you, so first of all, sorry for that. And I think it's probably best to just look at the example and understand. And maybe the best example to me, in order to observe what I'm going to talk about later, is P2 together with line and P2 is certainly smooth rational projected on the surface, and line plus is conic if we choose the line so that it intersects the conic in 2 points, is indeed normal crossing. And yeah, these components are net because they are just not have the same class. And anti-canonical, yeah, it's also checked. So the line
smooth.
Sorry?
The DIs are smooth.
Sorry, yes.
Okay,
I
so
assume, sorry, I didn't write it. I assume the DI smooth. Yes. So let's go where. Yes, the line is a representative hyperplane class and synchronic hyperplane class. So if we add this together, this gives minus is 3 times the height of point cloud, which is exactly minus the canonical. So this is what the anti-canonical is all about. Okay, so and now remember we had this geometry 1, geometry 2, geometry 3. So this is what you're about to see now. And the first geometry is actually super easy because it's just a reinterpretation of what we have here. So we look at the two together with the divisorial log structure induced by this divisor. Right. Then another geometry, and it will happen to be exactly the right choice. We can associate to such an input data is the following local Calabi-Yau fourfold. So what we do is we take the line bundle over minus the first divisor, direct sum, line bundle over minus the second divisor. So what we get here is something pilot over the base P2, and we take the direct sum of 2 line bundles. So each point has a 2-dimensional fiber, so until we can get it fourfold. The local is just to emphasize that it's not compact. So then you get confused with this. It's not too special. Okay. The third geometry is unfortunately a little messy. Maybe I should tell you how I think about this. So here, so what we did to go from here to here is we replaced the divisor with the information of the divisor with an extra dimension coming from taking the line bundle. Okay, we could go like half the way and just take the line bundle over the second or minus. Okay, and then we lift the information of the first remaining divisor to this 3-dimensional geometry, which is this L1. In order to do some calculations, unfortunately, I cannot just lift the divisor up. I have to do something. I have to decompactify the space. So basically, this is if I delete the line, I can just get 63 and triple vector bundle over this. And then the L1, you should think of replacing this line, which we just deleted, by a toric Lagrangian. So it's something real 3-dimensional in this case. Maybe for later purposes, just think of this as a replacement for the information of this device. Okay, so this this L1. No, I think it's S1 times R2 intersecting one of. So this picture is actually a little misleading. I think it's actually intersecting one of the fibers. I don't know how it intersects. Here, this 0 section. This I don't know, but
He's saying
not being extremely. Yes.
I mean, he's saying something correct, which is that ideally it should be.
Ideally, should be false.
Yeah.
Yes. I think you should think of it like this. At least this is how I always do.
And there are 2 of these, right? Can you take either?
Yes. So I took. Good question. So by convention today, we will always take the line bundle over the last one, and so this guy we want to be left with has to be a simple toric Lagrangian, and this, at least in the cases we looked at so far, had to come from toric divisor, which is why in this case we chose the line to be lifted and not this loop. Okay, thanks for that question.
So one more.
Yes. This should represent this line which I deleted. I replaced this line by Lagrangian, roughly speaking. At least this is how I think about it. Sorry. Fine? Okay, so in general, this was for our special case, but in general, we have L components, and so either I take the line bundle, the direct sum of all the line bundles associated to these components, take the total space, or I just take line bundle over the last and replace my information for the remaining divisors and lift them to the information of a Lagrangian. So this is how it works in general. All right. So far, this was geometry. Now we turn towards the definition of the invariants associated with these spaces. So X here should represent either this local two-fold, the L plus two-fold, or the three-fold. And what we want to do is we want to count curves in X. Okay, as I write it like this, it's of course far too naive because this number will be very much infinite. So we should fix some more data. So the first idea would be to fix the class of the curve in our target. And we can fix more. We can maybe restrict it to 0 curves. This is already hard enough to compute. However, it turns out that usually this is, first of all, written like this, of course, not very well defined and very infinite. So, another point I just wanted to make. So I lied a little. So I don't count embedded curves. I count parametrized curves. So I count so-called stable maps. So map from the stable curve into my target. Okay, now comes what I actually thought I wanted to say, namely that we have to put more conditions for our curve count in order to arrive at a finite number. So in this will be parts, something that depends on the geometry and an extra bit which we will work with. Okay, so for the local area two-fold, what we will impose for our stable maps is that the image here meets each divisor di with maximum tangency, d times di. So there probably I should explain a little what that means. So let's look at the case of YD. Again, 2 lines plus conic, and make our life easy, we just look at the case of D is just the class line. So then, since all lines in D2 meet, D times 1 is 1, and D times 2 is 2, because the 2 is 2 times type of length class. So this reformulated for our extra cases, number of lines in D2 intersecting D1 and meeting D2 tangentially. 1. Okay, so one curve that would contribute to such a count would be this one, right? Or this one, or this one. And I think you get the idea that for each point I fix here, I can just like take the tangent, and since all lines intersect, 2 will intersect 1. So I get a D1 pole of curves contributing here. So I get especially infinite. Not good. So in order to arrive at the finite curve count, what we do is we impose a point condition. So we say I want my line to pass through the generally chosen point in D2. And then it's not too hard to see that this is indeed a well-defined counting problem, and the result is 2. So we go back here to this last pseudo definition. We also impose point condition like these, certain number, so that we cut down the expected dimension of the counting problem to 0. So that we get a finite number here. Okay, so this was the local area two-fold, now the other two. And luckily, here for the local color area two-fold is this red star. It's just empty, so no extra conditions. Right, and here, yes, unfortunately, it's a little messy. To take whatever picture you like. So what we want to do is, I said that we lift the information of the remaining divisors and replace it with a Lagrangian. And we also want to replace the maximum tangency property with something appropriate here. So, and the appropriate lift of this condition is that we demand this stable map to have L, so this curve here, the domain curve to have L minus 1 boundaries. And with this, I mean real one-dimensional boundaries that if I draw my curve as a real two-dimensional manifold, this would be an S1 boundary. And I want L minus one of these. And each of these boundaries grab the Li d times di times. So with wrapping, I mean, so if I go around the boundary to the domain curve once, I want to go downstairs in the target d times di times around. This is what I mean with wrapping. And if you shrink the S1 together, it's exactly reproducing. It's like adding the cap on this one. Yeah. So it's the analog of maximum tangency, more or less. Okay, these are the counting problems. Maybe I should mention, because I get some questions about this. This modular problem is usually extremely ill-behaved, but there were clever people, you two, who figured out how to define curve count, which behaves in a way you would expect from physics, in order to make sense of this. Okay, good. And yes, so what we did was, so far we constructed 3 different geometries, 3 different illuminative invariants, which maybe at first sight then look super related, but not. That's the magic of log open. They are equal up to this factor. Yeah, so this was proven for quasi-tame Neff Loyenga pairs. Don't ask me about the notion of quasi-tameness here, please. By Bussobri Vangara, and conjectured for more general cases. And regarding generality, we could now maybe try to do some constraints here. And the thing I'm instantly looking at is the Gene zero condition. Can we maybe lift this log open correspondence to higher genes? And this is what the next slide is all about. So now look at the following counting problem. So we now want to count the D genes G, stable maps to X, with again roughly the same condition as before, satisfying the right number of factors, depending on the geometry. Okay, and just for convenience, we pack all these invariants together in the generating series, so H bar the form of variable, and we just sum up over all these numbers over all general. Okay, so I said that this red star is in both cases almost the same as before. So for the log color we have 3/4, it's indeed the case. It's exactly what we had before. For the log color we have 2 case, it happens that you have to place lambda insertion in your enumerative invariant, but this is just a technical thing. I don't want to talk too much about this, but more or less the counting problem type. All right. So, and now the magic is, for certain cases, these numbers happen to be, or these generating series happen to be equal, and they are related in almost the same way. So here we have the same factors as before, and the L factor gets deformed a little bit. So here numerator is the same, but the denominator here, this d times di intersection product, gets somewhat h bar deformed. People working from Witten theory can really meditate over this sign here and get an idea where it comes from. For probably everyone else, it's a little mysterious why there is a sign popping up if I go too high. But yeah, that's the magic. Oh, right. You might have wondering where's the middle, where's the local invariant, and short answer, there is not much to talk about in the middle, because the expected dimension of this counting problem in higher genus has negative expected dimension. So if I take degree of digital type or blah 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 blah, I always get 0. So nothing to compare against. But it's magic. It's still working for these 2 cases. All right. So let's see how this correspondence here works now in practice. And remember, this is a pretty straightforward looking formula. Right. Okay. Past me thought I should first drop the information that the right-hand side is governed by the figure topological vertex, very computational, very strong, while the left-hand side is, more or less encoded in the beauty of sketching diagrams and broken line state as a geometric, nice geometric computation, depending on who you ask. Okay.
Scattering diagrams are Feynman diagrams, therefore perfect for last week's workshop.
Yes. Right. So the magic is that also this formula, therefore, connects very different communities in research, more or less. So this developed, to my understanding, very much independently, and now we have a relation connecting it, at least in special cases for certain research.
But does the proof go by comparing those two boxes?
Yes, it's the proof. So here and here is direct computation. Brute force direct computation.
Okay. So it's you're not.
Sorry, I should say this holds for T and other invariant affairs, but is conjectured in larger generality.
But can I check so that the open invariants are defined? This is like they're defined in algebraic geometry, right? There's no.
Yes.
No. They're defined using topological vertex. Is that right? Like
no, it's they're defined in a way. It's quite interesting. So here we have a connection between relative invariants and open invariants, but the way these are defined rigorously, is via relative invariants. Because there is, I think, if the target is Q1, it's quite clear that there should be connection between open invariants to this target and relative invariants, where you fix ramification over one of the points. And then they, since this here is toric, this target, they define the invariance via torus localization. And they compactified one of the fibers that the Lagrangian intersected, they compactified it. So you get if you want. For this, you know that there should be some relative open correspondence. And in this way, they define something that matches the topological vertex. So therefore, geometric connection between these two sides, at least in my understanding, is not super straightforward. It's of the definition of this side.
I guess there's a more interesting point that Yannik is raising is that maybe there's a way of connecting the scattering diagrams in topological vertex. So that would be very interesting.
Yeah, I mean, I have no idea.
Yeah, maybe there was, I think there was recently this paper by Park.
That's right, yeah.
Maybe this could be
Maybe,
going in this direction. I don't know. I haven't. Okay, everyone happy? Everyone happy? Okay, again, back to back to our favorite example, 2 plus line conic. For convenience, I will just read, write the class instead of the actual divisor. And yes, okay, this probably tells you nothing now. So on the log side, I said before, you have scattering diagram to log broken line counts. This is scattering diagram with one wall for this counting problem here, and you have your broken line here, and then since it goes over the wall here, this uses you this binomial. I think if you have never done any of these calculations before, this is not telling you anything. I think the only point why I put this into this talk is the number of walls this green thing here, this broken line is crossing, is linear with the complexity of calculating this stuff. And I want to have some sort of comparison between the two sides regarding difficulty of how to compute. Here on this side, on the open Gromov Witten side, you draw a so-called toric tree graph, and then you apply the topological vertex to this, and this almost immediately to that. And here the difficulty grows with the number of vertices in your graph, more or less. So So far, pretty easy. This is the factor we've seen before, and yeah, match perfect. All right, so let's make it a little more complicated by blowing up a point here on the graph. Yeah, we take the proper transform of the line, and here the transform of that smooth representative. And what happens is we introduce a new wall in the sketching diagram. So spend one more time. This gives another binomial. Here we have two vertices now, two binomials. So far, same computation difficulty. Blow up another point. Not much is happening. We just add another wall here, another vertex. So they are equal via the then correspondence on the nose. But now let's have a little more fun. Blow up this point, yeah, and bam. Okay, yeah. Suddenly breaks loose, and you get countably infinite many lines here on this side, which produce you this awful sum here. So product, a lot of binomial coefficient, weird sum conditions, and apparently, since this side is still super easy to compute, apparently this object here is equal up to certain factor to this one. So and yeah, this was what Andrea Bini and I with a computational trick by Grafenthaler managed to prove in the end. And what's interesting is that the proof, more or less, the only important identity for this proof is just induction plus Q plus large summation. And that's a pretty simple combinatorial identity relating these intersection numbers. But yeah, this is the magic log local. Even though this side is maybe not very computable, this side just happens to be in most cases, and yeah, it gives you very surprising identities. Maybe if we have more complicated scattering diagrams here with, for instance, dense sectors of walls, maybe it gives rise to more, not gives rise, and maybe more complicated Q-hybrid geometric identities, which makes it also from the combinatorial level quite interesting. Good. And
just one question. So, what is this object on the right hand side? Can you define this one?
This here? Okay. This here is, remember that I said we take a line bundle over P2 and then we decompactify that using a line. So we get C2 plus another C direction. So this is the toric graph depicting C3. Each line here corresponds to one-dimensional torus closure. Yes, Schatten. So it's one of the fibers. It's representing one of the fibers, while this vertex represents the fixed point of the torus section. So if I blow up here, I still just delete this line. So I get this exceptional locus, which corresponds to this P1. So these here are always fibers. So these unbounded edges are always fibers, while these are P1s in the
It's like the
this is the skeleton for this toric color projected to 2 dimension. I think usually it's embedded in a 3 dimension, in the 3-dimensional lattice, but we project it down to the color Yao torus in this right logic.
So what's the red vector?
This represents the Lagrangian.
And it's not changing the variables, it just sits there.
Yes, it just sits like there more or less. So in the direction in which it sits, so I said earlier that the way these invariants are defined is by compactifying this to P1. And this direction here tells you how the normal bundle of this P1 in the compactified geometry splits. Like these here, I can't say it right away, but so looking at these and this vertex, you can instantly read of which normal bundle you have for this P1, and if you compactify, the direction also stores. Yeah, and every time we blow up, we get a new P1. That's it. All right. Yeah, and this is already the end point. I don't know if it's already, or we already talked too much. But yeah, main takeaway, let me stress again. So the log open correspondence between Gromov Witten invariants tells you how to trade contact conditions for higher dimension of the target. Remember, we replace the information of a divisor, which we use contact condition, with just taking the line bundle over this divisor and then use this as your target. And some remarks. So local open is proven for quasi-tame net Loyenga pairs, and you could ask now how many are there. So is it convincing? And yeah, it's 50. You can decide for yourself. This is convincing already, but yeah, the general conjecture is in the so-called Van Garel. And yeah, if you wonder how could we relax these conditions, we can pass that Y is smooth, but it's sufficient to have an orbit fault. And yeah, evidence for this is another work of the so-called Van Garel. And what's currently work in progress is that we want to relax the netness condition and replace it by a less strict probability. But if you don't have any questions, here are some. But I think basically all the questions I was thinking someone could ask already during the talk. So thanks a lot. It's quite nice with you. We still listening?
It's a surprising condition.
Yeah.
Not to ask.
When Navid was asking the question about this, very much at the beginning, I think, yeah, he was asking, can we also take this in conic? Sorry, can we also take the line bundle of the line, minus the line, and replace this in conic with the Lagrange? And the problem is we can only do this if we can deform that geometry to, I don't know which one we want to deform that. So we can only do this if we can deform to a case where then this divisor over to which we want to replace by Lagrangian becomes toric. So basically yeah, the notion of quasi-tameness is engineered so that all these quasi-tame Loyenga pairs admit such information. It's just re-expressed in geometric properties, but this is what it is, I would say.
Was the proof case-wise?
Case-wise. Yeah, a lot of work. Yeah, thank you. Thank you, here. He's representing these three people.
You're representing the middle guy.
Yes. Yeah, I don't know. Maybe I'm medium.
Sorry, I just missed the answer to that question. So he said he asked about how rigorously defining these open invariants.
Yeah.
And then he said, so just wanted me to clarify this. He said, oh, no, they're actually defined in terms of some relative invariant. You say that they're hard to say when it's just need to define.
I can try to explain what I think it is. Blah 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 blah. I think this I said earlier. So the way they do it is they can. Maybe I should.
You're still on this one. So and it's still recording, so you can just
I hope that people can also hear me, otherwise please.
or maybe it does it automatically. But anyways, yeah, but it's fine, you're being recorded.
Yeah, remember we had something like this. So this was our base. So the way these invariants are defined, so this is the toric skeleton. So these are the one-dimensional torus orbits. And so representing the type of this so one coordinate. So the way they define the invariance is they compactify this edge here. And so this arrow I was drawing before gets replaced by is used to say how the normal bundle of this now compacted one looks like. So what would that be? So this, I guess, would be I think it should be something like
I mean, if you think about if you close out the polytope, you get the polytope of P2, right? And then it's
yeah. So it should be that. Yeah. Maybe something wrong, but so you have a local one, and then I said we wanted contact condition to Lagrangian, and so we shrink this as one, around which we route, and then this gets replaced by prescribing ramification over this point here. So what you get is, so you define these open invariants for this case, for instance, as relative invariance of local Q1. They also have a particular choice of torus action, so that the end result is independent actually of choice of weights, I think. But this is approximately the way you would do it for this particular.
Okay.